That music that you're hearing was composed by Google's DeepMind team, and they are actually doing a tremendous amount of really interesting work in music and art and a number of other so-called creative endeavors. What I'd like to do is, first of all, say thanks for the opportunity to speak and the invitation to speak also. It's really great as a radiologist to be here at a personalized and precision medicine conference, because I think a lot of times people forget the value of diagnostic radiology, looking at genomic data. When people talk about personalized medicine, as was pointed out this morning, one of the points that people think about, their main point, is genomics or proteomics or metabolomics. But I would argue that if you're looking for complex, high-dimensional, and incredibly big data, actually radiology is even larger than genomics, and without the need to invasively biopsy or remove tissue, the potential to be able to take advantage of multi-parametric data in radiology is tremendous. But that's not what I'm going to talk about today. What I'd like to talk about today is artificial intelligence and how it's being applied to diagnostic imaging. And so I'd like to start out dedicating my presentation to all of the students and residents that have been writing to me in the last many months about, quote unquote, what they're hearing about the end of radiology. And here's a note from a first-year radiology resident in Portugal that's representative, and he essentially says he's been reading a lot about a number of projects like the IBM Avicenna project and a number of others. He says, I'm just 25 years old, I've got many working years ahead of me, and should I actually stay in radiology? And Andrea from Italy is a second-year resident in radiology, and she says in the last 3 months she's seen huge numbers of articles or discussions about machine learning. And bottom line, she asks, should I switch to interventional radiology to ensure a long career? And you really can't blame Zhao or Andrea about being concerned. Pretty much any time you pick up a magazine or a journal, everybody's talking about artificial intelligence and the potential of artificial intelligence to replace jobs. And particularly, depending on what you read, the first job that seems to go when people talk about jobs in The Economist and many other areas is the job of the physician, or specifically the job of the diagnostic radiologist. Elon Musk essentially, and as part of this hype cycle, Elon Musk is now saying we need to regulate AI before it's too late, and of course Stephen Hawking the same. With artificial intelligence in tones, Elon Musk were summoning the demon. And even Putin, is weighing in. So that's when you know we're really at the hype cycle. And Putin says, whoever has the best artificial intelligence will rule the world. So if there was ever anything that was hyped any more than AI, I'm not sure exactly what it was. Emmanuel, Ezekiel Emanuel, the architect of Obamacare, as many of you may recall, gave a talk at the American College of Radiology in 2016, proclaiming essentially the biggest threat to radiology was AI, and that radiologists may be replaced by computers in the next 4 to 5 years. And this is from Jeffrey Hinton, who you may recognize as a professor and probably one of the world authorities on machine learning, and now a Google employee. And he says if you work like a radiologist, or as a radiologist, then you're kind of like Wile E. Coyote in the cartoon. You're already at the edge of the cliff, but you haven't yet looked down, and there's no ground underneath. And so, in fact, his actual words were they should stop training radiologists now. What I'd like to do for Zhao and for Andrea and for everybody else is talk about why this is so incredibly silly, why we have the hype associated with it, and why the bottom line is that AI is going to be a tremendous tool, just like many other tools that we have. It won't supplant us, but we're going to use it in some really, really interesting, fascinating ways, and that we in healthcare are probably 15 to 20 years behind everybody else with regard to technology and implementation. Oh, and finally, a couple points. One point is the fact that just recently this week, they've announced a number of different new software programs that have emerged to actually replace AI developers. And so I find it somewhat ironic that there's now AI to replace all the folks in AI who are saying that radiologists will be replaced. And this is the other thing I get calls from are startup companies from all over the country and world. And this is from a CEO at a well-funded and well-known Silicon Valley startup from 3 years ago, who essentially said that he wanted to, quote unquote, get rid of the wasted protoplasm sitting in front of the workstation that's the radiologist and replace it with a much better and more reliable and consistent alternative in the next few months. And I'm sure you could substitute pathologist or dermatologist or many other specialties in that. And this isn't the first time that we physicians have been told that we're going to be replaced by a computer or by a machine. Back in 1904, the Watling Company said if you put a penny into the quote-unquote vibratory doctor, that it would put new life into you. Now, why the vibratory doctor doesn't have a shirt on and what exactly he does to give you new life, they didn't really specify, but fortunately in 1904 we weren't replaced by machines or computers, and I doubt we will anytime soon. You recognize HAL in 2001, A Space Odyssey, and also Ava from Ex Machina, and in general things kind of end badly for the humans whenever the AI systems in Hollywood end up getting smart enough to realize that they're kind of getting a bad deal from the humans. And even here we have Arnold.
Can't let you take the man's wheel, son. Now get off before I put you down. That I was bad to the bone, bad to the bone. That's it, goddammit. Bad to the bone, bad, bad to the bone. 1,000 hearts before I met you. I break 1,000 more, baby.
So sometimes in Hollywood, the robots are just really cool and not bad. So let's answer the question that Fred posed, and that is, what is and isn't machine learning? And I can tell you, among the medical students and colleagues that I have that I talk to, there's a lot of misinformation about what machine learning really is and isn't. And so let's go over some basic terms. There's kind of a general umbrella term, artificial intelligence. So we'll talk about that in just a minute. Inside of that are many, many different techniques, including machine learning, which is really one of many advanced statistical techniques to be able to look at patterns within data. And we'll talk about that in much more detail. Within that, there is a subspecialty or a subtype of machine learning that's referred to as neural networks, and within that, a subtype called convolutional neural networks or deep learning. And so that's kind of the Venn diagram of it. AI is basically an umbrella term for a variety of applications and techniques. I mean, people are selling calculators and pencils that are AI calculators and AI pencils, and everything that used to be kind of smart or related to computer science is now being called artificial intelligence. John McCarthy actually coined the term artificial intelligence, and you start seeing it in the literature around 1956. He complained that as soon as it works, nobody calls it AI anymore, and that's calculators that you can buy for $1 now are a great example of that. So there are three types of AI. The first is narrow AI, which is where we are today and where we probably will be for a long time, maybe forever, maybe a lot of years. And so we've got an artificial intelligence program that can beat the world's best chess champion, Magnus Carlsen, that you can download for free and run on a Walmart computer that'll play chess at about 3,300 or so, in comparison to Magnus, who's somewhere in the 2,800s or so. But that same computer is so narrow that it can't beat a 5-year-old at tic-tac-toe because it just doesn't know how to play tic-tac-toe. Speech recognition, translation, self-driving cars, Jeopardy, which I was a part of the Jeopardy team actually with IBM when they played the Jeopardy match and had the opportunity to work with them on looking at medical applications. And of course the assistants like Siri and Alexa and Cortana. So artificial general intelligence is potentially the next step, and that's kind of what everybody seems to be concerned about. That's where computers as smart as a human across the board, where it can reason and plan and solve problems and think abstractly. Jeopardy was thought and hyped in many ways as a general AI tool, but really it was very narrow, specifically to playing Jeopardy. Creating artificial general intelligence, much less artificial superintelligence, which is the third category, is a way harder task than creating artificial narrow intelligence. Will artificial general intelligence arrive when computers are as smart as we are? Well, there are actually conferences that are devoted to that topic. At a recent conference where that question was asked, 42% of the folks who were at the conference, who admittedly are somewhat biased, thought that general artificial intelligence would arrive by the year 2030. So that's 42%. 25% thought by the year 2050, 20% by the year 2100, 2% thought it's never going to arrive. So let's talk a little bit about machine learning. Machine learning, in many lectures that I've heard, at least in medicine, maybe not by the computer science folks, is kind of this little set of neurons, and the neurons get bigger and bigger, and you put more and more of them together, and you make computers faster, and you give it more memory, and all of a sudden, you've got kind of an evolving brain as time goes on. But that's not really what machine learning is, and machine learning, it's not that the system is a learning machine per se, it's a statistical technique. All statistical techniques learn when there's more data. If you have average, mean, median, mode, et cetera, they all learn because the more data you have, the more your statistics describe larger amounts of data. So I think a lot of people confuse the term for the type of equation solving that this advanced statistical processing can do. Fundamentally, all of machine learning is about recognizing trends from data or recognizing categories and making predictions from data. One thing that's important to remember is that there are thousands of machine learning techniques, not just one. And so regression techniques, neural networks, support vector machines, decision trees, Bayesian networks, many, many different types. And each one of those types can have a large number of parameters associated with it. So there's not any one technique that represents machine learning. Unlike data mining, machine learning focuses on prediction rather than discovery. And folks such as Leo Breeman and others have suggested that machine learning is really a statistical modeling paradigm, and it's kind of an algorithmic model. And some people have suggested calling it statistical learning rather than machine learning. So what is machine learning? Why the term machine? Well, it turns out that if you want to solve complex problems, like you're in the middle of a poker game, and you want to know what are the odds that I'm going to have the winning hand, sometimes it's easier, rather than creating a mathematical formula, to actually simulate it and actually do many, many simulation runs, build a machine. When I started out my residency, they said, oh, hey, you've got a background in computer science, you're in charge of making the schedule. And the problem with the schedule was it was really difficult because you had to take into account which residents didn't want to work with other residents and what attendings didn't want to work with which residents, and lots of really long set of rules. And there's no mathematical equation that was easy to derive for that. And so what I ended up doing is creating essentially a machine that created trillions of schedules, random schedules. And then it looked at the rules to see whether or not any one of those just serendipitously ended up meeting the rules. And after running the program for 3 or 4 days, it came up with some things that were pretty close to what the rules were. I gave it to my chief resident, who said, oh, like, your computer is the smartest thing ever. And the bottom line is it was completely random. But it was a machine built for a specific purpose that solved a problem. Simulation software, what happens if I buy another CT scanner or I hire another CT technologist? What's going to happen to my waiting room? Well, it's not really simple because there are lots of complex issues in the department that are bottlenecks rather than just how many patients I can scan. So we ended up creating, getting simulation software and simulated the department and started answering those questions. Let's say that we want to essentially do something like we want to have a 5-question survey for 10,000 people. And the object of the game is to, based on these 5 answers to the survey, answer the question, is the person taking the survey a male or female? Well, hey, maybe more females answer pink rather than blue. And these are all silly stereotypic questions. But how would you solve this problem if I asked you to figure out how could you figure out if a person were male or female? Well, you'd say, I'll do statistics, right? I'll do a correlation, I'll do a linear regression, maybe a nonlinear regression, and I'll go and do a statistical analysis. But what if it turned out that there were combinations that were patterns within those data? Let's say taller women under 200 pounds who prefer blue over pink prefer football, but only if they prefer Star Wars. Let's say that there were interesting patterns underneath that a statistical analysis would not find, but it turns out that machine learning is a really, really good technique to discover those patterns. Is this a beautiful pig or is it an ugly pig? Well, you probably have to ask a pig that, but if you were going to determine it based on eye distance to mouth ratio or eye distance to nose ratio, like we do in humans, then you might get a plot that looks like this, with the beautiful pigs in red and the non-beautiful pigs not in red. Well, try and draw a linear line around that, and where would you draw the line to separate the beautiful and non-beautiful pigs? And what would be the formula that you would derive for that? And what statistic could you use to describe that? And here's another example. You have the data itself. We humans can kind of see that there's sort of a heart shape in this, and we would say, hey, you know, if the thing falls outside of a heart, then it's probably not a beautiful pig. If it falls inside, it is. But how do you do that mathematically? So with a machine learning algorithm, you can actually solve the linear algebra problem that tells you that the shape of the data is x squared plus y squared minus 1 to the third power minus x squared y cubed equals 0. It would derive that formula in a linear algebra way in a real short period of time, only from the data itself. And so if we have a medical problem, for example, we've got malignant nodules versus benign nodules on a chest CT scan. Well, as the nodule gets larger, it's more likely to be malignant, and if it's kind of spiculated or not smooth and is irregular, it's more likely to be malignant also. But it turns out that the pattern is a lot more complex than that, because larger nodules past a certain point start getting smooth again. And so how do you describe the pattern of nodule size versus spiculation? Well, it's a really complex curve, and that curve can be described just from the data, and it can turn into a formula that might be used to predict future nodules. Well, why is it that you can derive these simple equations and that they end up being able to predict biologic systems? Well, here's an article that appeared from MIT that suggests most biological systems, like physics or astronomy problems, tend to follow relatively simple equations. So one of the questions is, well, then why is medical imaging thought to be so easy when it's actually one of the hardest specialties of all? Well, some of you may recognize this from your childhood, or if you've got kids, this is Highlights magazine. And if I ask a 5-year-old kid what's wrong with this picture, they're going to say, oh, there's a funny TV on top of the roof, and there's a big spoon and a fork and a snowman where there shouldn't be a snowman, and you guys could probably find 30 things that are wrong with this picture. But there's no computer algorithm or program anywhere that can beat a 5-year-old at what's wrong with this picture. If you pointed it to the fork or the spoon and you said, identify the objects in this picture, it would do a great job. It's about 97% now accurate. If you say what's wrong with this picture, no computer is able to get anywhere close. And that's a lot closer to what we in medicine, whether radiology or pathology or dermatology, et cetera, end up doing. So in Scientific American in the year 2011 in June, they suggested instead of the Turing test, which says if a computer could fool a human into thinking it was human, that's when general artificial intelligence has arrived. What they proposed was actually something much more akin to Highlights magazine. When a computer has the ability to know what is reality in the world and common sense and what belongs and what doesn't, that's when it will be. And you know, we've looked at a number of different approaches to being able to look at lung nodule identification. And if you take a look at this particular example, these are examples of lesions in the lung identified on CT, and the question is which ones are benign and which ones are malignant. And we can use a wide variety of different terms to describe those types of shapes and from a statistical or shape perspective. And the way that we've done it in the past has been to identify these parameters and then to correlate these parameters with whether a lesion is benign or malignant. But what if we could actually have the computer using a deep learning algorithm not worry about identifying these features or shapes, et cetera, but just look at the patterns of the pixels? What would happen if we took a picture instead of what I was talking about with machine learning and looked at every single pixel and made that a variable? And so that's what we end up doing when we're looking at a neural network. And so to solve image recognition problems, unlike the problem we had with the male versus female, in general, the best solution that we have so far looks to be a neural network. A neural network is very basically designed around a neuron, but a neuron is infinitely more complicated in real life as far as when it fires and when it doesn't and what it's connected to. But the simplest example is you have multiple neurons connected to multiple other neurons, and that's essentially what a neural network is trying to model. You could create a spreadsheet that would simulate a neural network. And if you did, you would have the columns on the right related to columns to its left, and each column would have weights or a multiplier assigned to it, a bias, which would mean an additive sum, and then something called an activation function, which is kind of the magic of these machine learning algorithms, which is a nonlinear function, like a sigmoid function or something that's called a rectified linear unit, where at a certain point the neuron doesn't even fire at all, but then when it fires to a certain amount with a certain formula. So with this small combination in the equivalent of a spreadsheet, what you then have happen is you know the input, you know the answer, and you just adjust all the spreadsheet multipliers and adders and essentially the activation function to the point where the input produces the output. And that's essentially the creation of a machine learning algorithm. The specific type of neural network that we use for image analysis is called a convolutional neural network. And we can apply that to, say, a picture, 240 by 240 pixels, which then has about 58,000 variables. And we can apply that for images of dogs and cats or images of medical images. So for Zhao and Andrea, if deep learning's been around since '43, why all the excitement now? Well, the reason was in the year 2012, the Toronto team entered something called supervision under Geoffrey Hinton, who I mentioned earlier. And the error rate for telling dog versus cat or person versus car versus helmet dropped from 26% in 2011 to now it's well under 3%. And so the improvement has been phenomenal by using convolutional neural networks. And so what we found was that inexpensive GPUs tied together could create the massive processing that we couldn't do decades ago when the theory was first introduced. And so a lot of the hype recently has been human vision experts who are carried away with the idea, which is really impressive, that you can identify something in a picture and come to the conclusion erroneously that you can identify what's wrong with the picture. And that's a fundamental flaw. There are a number of other issues as we try to bring artificial neural networks or deep learning into medical practice. One is, we're still struggling. How do we test human physicians and students for competence, much less how would we test a computer? If we had Robbie, the rapid reading radiology robot from 300 years in the future, how would we know that he was reliable? Would we test him on every single type of MR and CT and ultrasound and every disease? How would we debug Robbie, the robot from 300 years in the future? And how would we get FDA to clear Robbie, the robot? And so, some reasons that I think we physicians won't be replaced anytime soon, including, this is kind of the old joke, isn't it wonderful about standards nowadays? There's so many to choose from. And that same irony kind of applies to machine learning algorithms. It's not clear which one works and which doesn't. Another issue is this black box nature of deep learning. We can put in an image. We know the answer that comes out, but in general, we don't know exactly what the logic was. There's no if-then statements. And so getting FDA clearance on something where you're not sure exactly how it works is an issue. A lot of these systems are very brittle to very small perturbations, meaning if I scan something on my CT scanner A and I create essentially a learning or training set, it may not work on my CT scanner B, even though to me as a human it looks identical. Here's an image on the left with a computer saying it's 60% confident that's a panda bear, which it turns out to be, as you know. Then you do a little noise in the background that we can't even perceive, create the image on the right, and now the computer is 99% sure that this is a gibbon. And so these systems are, because they work in non-intuitive ways, can come up with some really significant issues. In fact, computers even have some problems with recognizing anatomy. So the adrenal on CT scans is a notoriously difficult problem for computers to find. And so I actually have been in debates where I was told, well, gee, now I've got to wash somebody's car. I had a challenge out throughout the world that anyone who could find the adrenals better than a fifth grader, I would wash their car. And so at a recent debate that I had here in Chicago, or about a year ago actually, Ron Summers, who's at NIH, had a 68% accuracy in actually finding the adrenals. That's called a Dice coefficient, essentially. And so here's my
Hi,
response.
I'm Faris Siddiqui, and I'm in 5th grade, and I'm going to find the adrenal gland on a CT scan.
It's a local Chicago
I
boy,
have
by the
not
way,
seen
in
these
5th grade.
cases before. So on here, this is the left adrenal gland, and
So this is after about 15
This is
minutes
the
of training
right
for a 5th
adrenal
grader.
gland.
So yay humans, his DICE coefficient would be a lot closer to upper 90 percentile or so. And so, at this point, there are literally tens of thousands of papers that have been written on fracture detection and brain hemorrhage and mammography and multiple sclerosis and bone age determination and lung nodule detection. The problem is that in order to validate algorithms, you need to have not just tens of studies, as we do when we train a human, but thousands or millions of studies to actually be able to reliably train a machine learning algorithm. And that's a major expense and very time-consuming also. The other challenge is, how do you deliver all these algorithms? There are tens of thousands of papers that have been written in research conferences, but yet when I sit down at my workstation to do interpretation, I have practically none of those, not even 1% of 1% of what's out there available to me. And so it's a challenge figuring out, how do you get those and deliver them? What are some of the challenges outside of medicine that have been most impressive? Well, some of you who've been around for a while have probably had the opportunity to play Atari video games. There's a little joystick and a little red button, and there's 70 games. How would I teach a computer how to play all 70 of those games? Well, the old school way would be, for each game, you would teach it the rules, and you would end up creating a strategy around each game. The DeepMind team didn't do that. They essentially used a machine learning algorithm, and they ended up essentially just having the computer experiment on its own. It knows the score, and it can control the paddle, and that's pretty much all it can do. After a while, it learns the basic thing that if the paddle is somewhere close to the ball, then it's probably going to get a better score. And so after a couple of hours of playing by itself, it starts playing like an expert. So all it's doing is it's looking at every state, every fraction of a second, and looking where all the pixels are, and it knows the score. And after 2 hours, it's learned essentially how to move the paddle to hit the ball. Now, after 4 hours, it comes to a really interesting insight that it then remembers from then on. And those of you who are expert breakout players essentially know that what you want to do if you really want to rack up a score is what? Anybody? Break through the wall, right. So what the computer learns after 4 hours of playing is, let's break through the wall and get to the back of the wall. So it tries to angle the paddle in such a way that as early as possible it breaks through the back, and there you go. And it knows that. So from then on, it remembers within the matrix, within that spreadsheet I was talking about, it remembers that particular strategy. It was said that the game Go would not be mastered by a computer until the year 2030 or so. And here we are, it was just recently, last year, that Leo Siegel from Korea was bested by the DeepMind program that played Go. And recently, just in the last literally few days, they created a new program that wasn't trained on human games at all, but just literally started from scratch. Didn't learn from the previous thousands of games that the first version, AlphaGo, learned from. AlphaGo 0 just literally started playing itself without any humans. And recently, the AlphaGo 0 beat AlphaGo, that beat the best human, 100 games to nothing. And at this point, the DeepMind team has just essentially stopped playing Go because it's so advanced at this point. This is my car driving across what some people consider the scariest bridge in the United States between eastern and western Maryland, the Chesapeake Bay Bridge, if you're familiar. You see it careening back and forth, but that's the camera, not the car, careening back and forth on the bridge. But would you trust a car to drive across that bridge if I told you it was 5 times safer than the typical driver, but that when it makes a mistake, it's a really bad mistake and it makes a sharp right or a sharp left turn off the bridge? And how do we essentially debug medical programs and know when they're right or wrong, and how do we debug a self-driving car? So there are major regulatory and medical legal challenges that would be associated with a computer doing image interpretation. This article in the Harvard Business Review suggested that although computers will get really good at making predictions, we're going to need humans for judgment for a long, long time. And so I think I'm going to stop there. I wanted to kick off some ideas for maybe discussion related to AI. I'm really looking forward to the next couple of talks myself, and then would love to hear some comments or questions from you all. So thank you very much for the invitation. Appreciate it.